If you need help with the force of friction practice, the practice sheet that followed our force of friction lab, this video is for you. The first page is for CP, and then the last page is for honors only. So we'll start with the CP part, and then I will add the honors part, so CP will be free to go once we're done with this first page. So we have a 5 kilogram object is resting on the floor. The force of static friction is 20 newtons. First off, if it was just resting by itself with no force of pull, remember it wouldn't have any force of friction acting on it. Because remember, force of friction is a lazy force. It only exists if it has to. So if we have some sort of a pull or a push on an object that is not moving, we know that our force of friction equals the push or a pull. So again, if I were just to show you the forces on an object that is resting without being pulled, I would just show mg. Equal to it would be normal force, and that would be it. They're telling me that there is a 20 Newton force of friction. So I'm just going to say it's this way. So why would force of static friction exist? Obviously something is pulling on the object. So this force of pull, even though it's not mentioned, it exists there. The question for this problem is about mu static, so coefficient of static friction. In the lab, we talked about how force of friction depends on the surface. So this right here, mu s, the coefficient of static friction, is what characterizes how rough the surface is and how much friction it will have, times normal force. That's the formula. So we are after mu static. So we're going to take our force of friction static, which is given to be 20 newtons, and we will divide it by normal force. Well, what is normal force? In this situation, if the object is flat on the surface, it's just going to be equal to force of gravity. And since it's 5 kilograms, we're going to multiply 5 times 9.8 because that is the force of gravity. So I can also write this as mu static times mg. So then you grab your calculators and divide 20 by 49, which is 5 times 9.8, and you get 0.41. Now mu doesn't have any units because when you think about it, you took 20 newtons, you divided by 49. Also newtons. Newtons over newtons give you nothing. Coefficient of static friction is just 0.41. Force of friction is 41% of normal force if you're into percent. Anyway, then we have example 2 is very similar to this one. Only now they're not giving us the actual force of friction. They're saying that the object is being pulled with a constant speed, which is very, very important. Then that tells me that the pull is equal to friction. So they technically tell me that force of pull is 30 newtons. And because of V equals constant, since velocity is constant, then force of friction kinetic is also 30 newtons. So we are after mu kinetic in this case. So we're going to take force of friction kinetic. We'll divide it by force normal, which will be, again, since it's flat on the ground, it's basically just mass times g. So 30 over 98, and that is 0.31. Again, no units. This is just a coefficient. Example 3. So here, this is critical thinking. You need to figure out if the object will move or not. So what we do know is that there is a force of pull of 55 newtons. We are given two coefficients, the static and kinetic, and we know from the lab that mu static is greater than mu kinetic. And in general, static friction is greater than kinetic friction. And also from the lab, you remember to move an object, force of pull should be greater than force of static friction. It's not greater, then the object will not move. And force of static friction, remember, is the lazy force. It will only give us as much counter force as it needs to keep it from moving, to keep the object from moving. But it also has a maximum, and once you outpower the maximum, force of static friction is going to let go and the object will start moving. So what we need to figure out is how much force of friction maximum these two surfaces are capable of producing. So we're going to use mu static times normal, and if it's flat, I want you to draw the free body diagram. So you're going to draw this. I'm going to just cheat a little bit and duplicate it. You go ahead and draw it. Force of friction static, which is, I'm going to look at my 0.42, because this is the static friction, times 15 times 9.8 is 61 newtons with a little tail. And that is greater than force of pull. Again, this is maximum. While it is being pulled with 55, that force of static friction is exactly 55 newtons, but it's capable of producing 61. So 55 is not going to outpower force of static friction. So therefore the object will stay in place. Now look at how for example 4, I'm keeping the same object with the same coefficients of friction. However, now my pull is 65. Real quick, since force of static friction was maximum of 61, then I know that my object will be moving because I had outpowered it with 65 newtons. Since static friction is outpowered, it is no longer at play. Instead of force of static friction, I'm going to draw, and I know it's going to be less. It's going to be friction kinetic. Net force equals mass times acceleration. So it moves for sure because pull is greater than static friction maximum. And since it's going to be outpowered, then it will be replaced by kinetic friction, and kinetic friction is less. I need to know how much kinetic friction I'm talking about, because in order to figure out my acceleration, I will need to subtract force of kinetic friction from pull. Force of kinetic friction equals mu kinetic times normal force. So I'm going to take my 0.37 and multiply it by 9.8 times 15 gets me 54.4 newtons. Acceleration will be, I have 65 of pull, 54.4 of friction, and I divide all of that by mass, which is 15.71. Since it's acceleration I'm looking for, it's meters per second squared. So that's your answer to question number 4. Question number 5, they are giving us the acceleration and they want us to find the mu k. The picture, or the free body diagram rather, will be the same. And I already got a little bit lazy here because I forgot to erase this, because now my force of pull is 65 and my force of friction is now 54. But you don't really need the values. You need to label the forces with the names. So pull minus friction. Force of pull minus force of friction, kinetic, is going to give me mass times acceleration. And they actually give me the acceleration. I also know that force of pull is 175. I need to find force of kinetic friction, and I will find it as force of pull minus my net force. So it's 175 minus mass is 35. And acceleration is 2.2. So when I do 175 minus 2.2 times 35, that gets me 98 newtons. Is just mass times g, right? So then mu kinetic will be 98 over 35 times 9.8. So look at this. So it's basically like 10 divided by 35. 10 divided by 35 gets me 0.29. 0.29. And again, this doesn't have any units whatsoever. From here, CP students, you are free to go. Honors students, we continue. So what we have here is now we have an object that is being pulled with a force that makes an angle with the horizontal. Of pull is at an angle. So let me start with force of gravity, because that's a given. It's mg, and then I have my force of pull at 30 degrees, so something like that. Since it is at a certain angle to the horizontal, I'm going to look at my force of pull in two directions, vertical and horizontal. And remember, normal is now less than gravity, because force normal plus Fpy should be equal to mg. Now Fpy I can find as 175 times sine of 30. Sine of 30 is 1/2, so I take, that's my Fpy. Then force normal from there is going to be 35 times 9.8, which is force of gravity, subtract 87.5 from it. 35 times 9.8 minus 87.5 gets me 255.5 newtons. Then force of friction, it's going to be kinetic, obviously, because it's being dragged, and it's dragged with acceleration. We're looking for acceleration. It's going to be mu k times normal force. So make sure you don't make a mistake in this question, because it's no longer, normal force is no longer force of gravity. Mu k is going to be 0.3 as they gave me, and my normal is 255.5 newtons. So multiplied by 0.3, that gets me 76.65 newtons. Now I just need to compare my force of friction, kinetic, to my force of pull X. So force of pull X is going to be 175 times cosine of 30 degrees. So 152 newtons is my FPX. Then if I want to find my mass times acceleration, which is net force, I will take FPX and I will subtract force of friction, kinetic, from it. So it's 152 minus 76.65 is 75.35. From here, acceleration, according to Newton's second law, is net force 75.35 over mass 35. So about 2.2 meters per second squared. And it accelerates in the direction of the pull. So here we have below the horizontal force. I will have to rearrange. So instead of subtracting from gravity, I have to add it to gravity now. Because see how it's pointing downwards? So then in this case, my force normal is going to be mg plus fpy. That gives me 219.5 newtons. That is my normal. From there, I can say that my force of friction, kinetic, is going to be 0.37 times 219.5. It's going to be 81.2 newtons. But here's the deal. How do I know if I need to go ahead and find my acceleration yet? If they ask me, will the container move? And if yes, find the acceleration. So I kind of jumped the gun here. Do not do that. Will the container move? Before you find kinetic friction, find static friction first. That would have been 0.52 times 219.5. 114.1 newtons. So let me compare that to my pull of X. 145 cosine of 30 degrees is going to be 125.6 newtons. So I can say about 126 newtons. All right then. Yes, it will move. So then to find acceleration, it's going to be net force over mass. For net force, I'm going to take my force of pull X, which is 126, and I will subtract my kinetic friction from it. Gets me 2.963 meters per second squared in the direction of your pull. Very last one. And we need to figure out if it's going to slide or not. And if it does slide, what is the acceleration? Remember in the lab for friction, what you did was you lifted the incline until it moved. And then you figured out your mu s. Your mu s was mgx over mgy. Why is that? Because when you have something on an incline, your normal force is the y component of gravity. And if it's still at rest, you had force of friction, static, equal to mgx. This was mgx, this was mgy, this is the actual mg, this is normal force. That's your free body diagram for an object on an incline that is at rest. Mg sine of theta over mg cosine of theta. Ultimately, that gave us tangent of theta. That was your mu s. If I look at this, angle is 15 degrees. What is tangent of 15? It's 0.26. Well, actually 0.27 if you round it correctly, which I didn't, but 0.27 would be your mu s, needed coefficient of friction to stay in place. Yours is actually bigger than that. Your mu s is 0.43. So definitely will stay on it. If, however, you forgot how we did the lab, you can still do it the full way. It will slide if force of gravity X is greater than force of friction static maximum. What is my force of friction static maximum? It's going to be 0.43 times force normal. 0.43 times 3 times 9.8 times cosine of 15 degrees. Because remember, this is your normal force. Gets me 12.2. So 12.2 newtons is your force of friction static. Then what is my mgx? Mgx is going to be 3 times 9.8 times sine of 15 degrees. That is 3 times 9.8 sine of 15. That gets me 7.6 newtons. So this downward force of mgx is actually less than the maximum force of static friction. So the object is going to stay at rest and it's not going to slide down the incline. That's how you answer question number 7.